Hello all, welcome to GATE Digital Electronic Devices. And last classes we have seen about the diode operation and diode characteristics in forward and reverse bias, and we have seen the junction capacitance in forward bias and also in reverse bias. And today's class, let us learn about the diode current equation and also the effect of temperature on the characteristics of PN diode. So, and also let us solve some problems, important problems which are coming in GATE examinations and also in competitive exams. So, let us see and go with the diode current equation. As we have learned about the diode current equation and the diode forward bias characteristics, this is a diode structure where this is a p type and this is an n type. This is a depletion region. This is the depletion region where the charge carriers flows from p type to n type and also from n type to n type to p type in forward bias. So therefore current flows in forward bias due to majority charge carriers, and also current flows in reverse bias due to minority charge carriers. So as you see here, what is this diode current equation means? Actually, first you consider here the diagram here where it is x is equal to 0. I am considering this one as Pn of x, where in n-type semiconductor the majority charge carriers are holes at a distance of x. So at x is equal to 0, this is a junction where you get a junction J, where this is a p type and this is n type, where the majority charge carriers moves from p type to n type. So all these majority charge carriers are holes here. There are also some minority charge carriers here in p type. Those are nothing but electrons. So holes are majority here and electrons are minority charge carriers. So all these holes tries to move from p type to n type by applying some external potential, which is nothing but forward voltage Vf. So as holes moves from this point to this point, they gradually enter into n-type semiconductor, where here majority charge carriers are electrons and minority charge carriers are holes. So therefore here all holes will move and cross the junction. So therefore if they cross the junction, they slowly recombine with the holes electrons present in n-type semiconductor. So what happens is, so this recombination, as the distance increases from x equal to 0 towards right side, what happens is the recombination of the charge carriers decays. The recombination of charge carriers decays like this, but they are not becoming 0, they are decaying, because actually this is the concentration of minority charge P in n-type semiconductor at thermal equilibrium. It is called room temperature. So this is a minority charge which is present in n-type semiconductor. This minority charge will be present here, which is nothing but hole concentration. So all holes will move from this type to this side, and therefore it decays here. So this is a gradual decay of holes, majority charge carriers, which are entering from p type to n type. And the same similar case, while the electrons are jumping from n type to p type, the same similar case you get like this. The same similar case, they gain decay, and therefore it will reach the thermal equilibrium position here. So this is the thermal equilibrium position, where you get here the minority charge electrons, because this is p type semiconductor, in p type semiconductor at thermal equilibrium position np naught. So if you combine both the cases, this case and this case, which is this case is called as the current produced in n-type semiconductor, the current produced due to holes in n-type semiconductor. Then here, according to here, the current produced due to electrons in p-type semiconductor. Then if you combine this one, where the majority charge carrier current I get here IPN plus INP, it is due to majority charge carriers and also due to majority charge carriers of holes and also due to majority charge carriers of electrons. So I get here one equation. That equation is I is equal to I naught into e power v by eta vt minus 1. So this is what called as the diode current equation. I is called as the forward current. I is called the forward current, and I naught is called the reverse saturation current. I naught is called the reverse saturation current, which is given by I naught is equal to AE dP Pn naught divided by LP plus AE dN NP naught divided by Ln, where A is the area, E is the charge of the carrier, dP is diffusion constant of holes, Dn is diffusion constant of electrons, Pn naught is concentration of holes in n-type semiconductor thermal equilibrium, concentration of electrons in p-type semiconductor thermal equilibrium, Lp is diffusion length of holes and Ln is diffusion length of electrons. And similarly here V is called applied potential. From that equation we have V is equal to applied potential or applied voltage, and neta is nothing but a constant, which is 1 for germanium and it is equal to 2 for silicon, and Vt is nothing but volt equivalent temperature. Vt is called volt equivalent temperature. Vt is called volt equivalent temperature, and already we have known this formula, which is equal to kT by Q. K is Boltzmann constant, T is temperature, Q is the charge, and if you substitute K and Q value, you get T by 11,600. And at room temperature, it is equal to 26 millivolts. At T is equal to 300 degree Kelvin. We already proved all this, right? So this is called as a diode current equation, what we have got. So if you apply forward bias, then you can apply here V can be taken here in this equation. For forward bias, V can be taken as plus V, and if it is reverse bias, V can be taken as minus V, because negative voltage we are applying for reverse bias. So therefore in the same equation you can write it as minus V, then it applies for reverse bias. Okay, right. Now let us see in deep into this diode current equation. So we have got an equation which is called I is equal to I naught into e power V by eta Vt minus 1. V is equal to, for forward bias, V is equal to Vf positive voltage. For reverse bias, this is for forward bias, so V is equal to minus Vr, this is for reverse bias. So substitute V value as Vf for forward bias, V is equal to minus Vr for reverse bias, right? So this is what the diode current equation. Now we have two resistances in diode. One is called static resistance and one is called dynamic resistance. We have static resistance and dynamic resistance. Dynamic resistance is given by small r, static resistance is given by capital R. Static resistance can be defined as R is equal to, it's a ratio of voltage to current. R is equal to V by I. It's a ratio of voltage to current. So and it is defined in terms of ohms. But what is dynamic resistance? Dynamic resistance R is nothing but change in it's a ratio of change in voltage to change in current. That is R is equal to dV by di. That is equal to, we can write this one as change in voltage divided by change in current, or it can be written as V2 minus V1 by I2 minus I1. Okay. So therefore, now let us find what is dynamic resistance from this diode current equation. R is equal to, I have dV by di. So where you can differentiate the current with respect to voltage. So but I have here the diode current equation as I is equal to I naught e power V by eta Vt minus 1. So partial differentiate the above equation with respect to V. So what I get here, I get di by dV is equal to I naught into e power V by eta Vt into 1 by eta Vt minus constant value is 0. So therefore I get here di by dv as di by dv is equal to I naught into e power v by eta vt whole divided by eta vt. But from this equation, from the first equation, from this equation, if I can split into two parts, I is equal to I naught into e power v by eta vt minus I naught. So therefore, bring this I naught that side, I plus I naught is equal to e power I naught into e power v by eta vt. So instead of I naught into e power v by eta vt, I can write it as I plus I naught. So therefore, from this equation, I got di by dv is equal to I plus I naught divided by eta vt. But if we compare with I and I naught, I is called majority charge carrier current, I naught is called reverse saturation current. So always remember, I current is double greater than I naught. So therefore, if I is double greater than I naught, because reverse I naught is reverse saturation current, it is in microamperes, whereas I is in milliamperes. So I is always double greater than N. So therefore, I can neglect the reverse saturation current and I can get only I value as I is divided by eta Vt. So substitute this value here in this equation. So dynamic resistance R is equal to, you get here eta Vt divided by I. This is the dynamic resistance what we have got for a diode current equation here. Using the diode current equation, we have got R is equal to eta Vt divided by I. And the static resistance is R is equal to V by I. Dynamic resistance is also measured in ohms. It is dynamic resistance is measured in kilo ohms or sometimes mega ohms also. Okay, next let us see the concept of temperature dependence on VI characteristics of a diode. As you see, VI characteristics, we have drawn and learned VI characteristics of a diode, where in forward bias, a forward voltage and a forward current we have applied. We have got a graph like this, and this is called as cut-in potential V gamma. And the reverse bias also we have got, where the current gradually increases and at some particular point you get breakdown voltage VBR. So therefore, this is called as reverse voltage VR, and this is IR, which is in microamperes. Now these characteristics depends on temperature. So how do you say these characteristics are depends on temperature? Means, so this characteristics first in these characteristics, the temperature will affect the reverse saturation current I naught, because this is the reverse saturation current I naught where it is affecting. So I can say that in the diode characteristics, temperature depends or reverse saturation current depends on temperature, or we need to learn about the effect of temperature on reverse saturation current I naught. Reverse saturation current I naught. And the second case, we can also learn here the effect of temperature on, the second case is the effect of temperature on forward voltage V, Let us see some important concepts here, how this temperature affects this reverse saturation current I naught and the forward voltage V. So as we have an equation for I naught, first if we go with effect of temperature on reverse saturation current I naught, so we have an expression in the equation I is equal to I naught into e power V by eta Vt minus 1. We have got I naught value as I naught is equal to Ae dP Pn naught divided by Lp plus Ae dn Np naught divided by Ln. So this reverse saturation current is being affected by the temperature. How it is affected? So you need to find here the relative temperature coefficient, which is nothing but 1 by I naught into di naught by dt. So from this derivation you get an equation which is nothing but 1 by I naught into di naught by dt as m by t plus m by t plus neta Vt divided by capital T, m into m by t plus m into neta into Vt, m into neta into Vt into m divided by t, where this m is called constant and it is varying for germanium and silicon. For example, we have two diodes, germanium and silicon. Capital M is equal to, for germanium it is 2 and for silicon it is equal to 1.5, and neta it is equal to 1 for germanium and 2 for silicon, and capital T is the temperature and Vt is the room temperature. So therefore here capital M by T plus neta into Vt, capital M by T, sorry, this equation is capital M by T plus Vg naught divided by neta Vt capital T. So this is the equation for relative temperature coefficient on reverse saturation current. So we get Vg naught is equal to, for germanium it is 0.785 electron volts and it is equal to 1.21 electron volts for silicon. So if you substitute all these values, into this relative temperature coefficient, then you get like this. So for germanium 1 by I naught into di naught by dt, 1 by I naught into di naught by dt for germanium. So you get here m by t, capital M is 2 divided by t, t is 300 degree Kelvin at room temperature, plus Vg naught is 0.785 divided by neta is 1 for germanium into Vt 26 millivolts, that is 0.026 into capital T is 300 degree Kelvin. That is equal to, if you substitute it, you will get here as 11% here. You will get here 11% per every degree C rise in temperature. That means germanium diode, its reverse saturation current changes by how much quantity, means 11% for every 1 degree C rise in temperature. And similarly, for the same formula, if you apply find the relative temperature coefficient 1 by I naught di naught by dt for silicon diode, then you get here m by t, m for silicon it is 1.5 divided by t, temperature T is equal to, actually it is 27 degrees C, convert into Kelvins, then you will get 300 degree Kelvin plus 1.21 whole divided by neta is 2 into 0.026 millivolts into 300 degree Kelvin. That is equal to, you get here 8% for every per degree C rise in temperature. That means silicon diodes varies with respect to how much quantity, means for every 1 degree C rise in temperature it varies with respect to 8% of reverse saturation current. So this is what the temperature dependence on germanium and silicon diodes. But on an average, considering these two into consideration, on an average for both germanium and silicon, we can take as 1 by I naught into di naught by dt changes relative temperature coefficient is taken as 7% for every degree C rise in temperature, because there is some leakage, there are some leakage currents which are observed by the materials which are laid on surface of the diodes, both germanium and silicon diodes. So some leakage currents will be observed by that surface impurities. So therefore you get here the reverse saturation current as 7% per every degree C rise in temperature. So therefore I can consider now the relative temperature coefficient for both germanium and silicon as 7% per every degree C rise in temperature. So if it is 7%, then what happens? See, for example, for every 1 degree C rise in temperature, what happens is reverse saturation current changes by 1 plus 1%, 7%, 1 plus 7%, that is equal to I naught changes by, because we are adding it to 100%. So this is 100%. This is 100% plus 7%. So therefore 100% is nothing but 1 plus 7% is 0.07 of I naught. So therefore I naught is equal to changes by 1.07 of I naught. So for every 1 degree C rise in temperature, I naught changes by 1.07 whole power 1 of I naught. Similarly, for every 10 degree C rise in temperature, reverse saturation current changes by 1.07 whole power 10 of I naught. So that means 1.07 whole power 10 is approximately equals to twice of I naught. So that means an important expression comes here. For every 10 degrees C rise in temperature, reverse saturation current becomes double. Reverse saturation current becomes for a double for a diode. Very, very important equation where we need to learn. So that means reverse saturation current becomes double for every 10 degrees C rise in temperature. Suppose it's been asked for 30 degrees C rise in temperature, then the competitive questions like this. Question comes like this: I naught is equal to 1.07 whole power 30 into I naught. So you can able to find what is the value of 1.07 into I naught, then you can easily find the answer. So but you need to remember this expression, that is 1.07 whole power 1. 1 is 1 degree C, 10 is 10 degree C temperature, 30 is 30 degree C, 20 is 20 degree C rise in temperatures, likewise. Okay, now let us see what is the effect of, for second case, effect of temperature on forward voltage. What is the effect of temperature on forward voltage? What is the effect of temperature on forward voltage? So here we need to find the change of voltage, forward voltage with respect to change of temperature. That is dV by dt we need to find here. So as you do derivation for this dV by dt, we have got the expression for dV by dt as V minus of Vg naught plus M into neta Vt whole divided by capital T. This is the expression what we have got. If you derive the temperature, effect of temperature on forward voltage, dV by dt is equal to V minus of Vg naught plus M neta Vt divided by capital T. So the same thing here we have already mentioned here for germanium and for silicon. And for silicon, capital M is equal to 2 for germanium, 1.565 for silicon. Neta is equal to 1 for germanium, 2 for silicon. And Vg naught is the energy gap, which is equal to 0.785 electron volts for germanium and 1.21 electron volts for silicon. And this is called applied forward voltage or cut-in potential. V is nothing but cut-in potential or cut-in voltage, where this is equal to 0.2 volts for germanium and 0.6 volts for silicon. And T is the temperature. At room temperature 27 degrees C plus 273, then you get here 300 degree Kelvin. Temperature is 300 degree Kelvin. T is equal to 300 degree Kelvin, right? Now substituting all these values for germanium and silicon, I got here dV by dt for germanium is equal to, first apply cut-in voltage for germanium, V is equal to 0.2 volts minus of Vg naught 0.785 plus capital M2 neta 1 Vt at room temperature. Vt is equal to how much? T by 11,600. T by 11,600. T is 300 degree Kelvin divided by 11,600. Already we have found here this is equal to 0.026 volts or 26 millivolts. So therefore substitute here Vt value 0.026 whole divided by temperature T is 300. So you get a value of here as minus 2.1 millivolts per degree C. Similarly, if you apply for dV by dt for silicon, then you get here 0.6 volts. The same formula apply for germanium silicon values, 0.6 minus of 1.21 plus M value is 1.5 into eta value is 2 into 0.026 whole divided by 300. So you get an answer as minus 2.3 millivolts per degree C. So but on an average, both for germanium and silicon, on an average, both for germanium and silicon, you get here for germanium and silicon, you get the change in voltage with respect to temperature dV by dt as it can be taken as minus 2.5 millivolts per degree C. Minus 2.5 millivolts per degree C. Right. There comes here very important points that are to be studied here, which is dV by dt, which is change in voltage divided by change in temperature, and it can be written as change in voltage divided by change in temperature means it can be written as V2 minus V1 divided by T2 minus T1, that is equal to minus 2.5 millivolts per degree C, minus 2.5 millivolts per degree. So if you know any value here and any unknown value is there, V2, if we know T2, T1 and V1, we can able to find the other voltage, which is nothing but V2 voltage, or if you know T2, V2 and V1, we can able to find T1 temperatures. So this is a very important expression, V2 minus V1 divided by T2 minus T1 is equal to minus 2.5 millivolts per degree C. The similar thing here, you can observe here, as temperature rises, what happens here? As temperature rises with respect to characteristics, first we can have this one here. This is a minus 75 degrees C because it has been decreased, so therefore cut-in voltages increases here. As temperature decreases, cut-in voltages V gamma increases. So see here, this is a cut-in voltage if it is minus 75 degrees C, and the same the reverse. This is a graph for this one is minus 75 degrees C. This is existing for minus 75, which is a reverse bias characteristics, right? And the breakdown voltage is very less here if temperature is decreased. And similarly at 25 degrees C here, this is a cut-in potential where it's been decreased, because as temperature is raised, so V gamma definitely decreases, definitely decreases. And you can see here, as temperature is raising, then cut-in potentials are decreasing here, and it is going towards the x is equal to V equal to 0. So therefore the cut-in potentials decreases as temperature is rising here. And similarly here, as temperature is rising, the graph here, the breakdown voltage increases here, and therefore the graph goes like this. See, it is going for microamperes. This is for microamperes, and this is for nanoamperes, and this is for picoamperes likewise. See this, the graph goes like this because its breakdown voltage goes on increasing, right? And the same thing, if I know here two reverse saturation current which are called as I01 and which is produced at a temperature T1, reverse saturation current I02 produced at temperature T2. I have a specific formula here not to have or to find the temperatures or reverse saturation currents. Suppose if I know this one, and this one, I can able to find reverse saturation current at temperature T2. I02 is equal to, it's been given by I01 into 2 power T2 minus T1 divided by 10. This is a formula which has been applied for finding out different reverse saturation currents at different temperatures. A very important formula. I02 is equal to I01 into 2 power T2 minus T1 divided by 10. So this is a very important formula here, right? So these are all the important formulas and the graph which is affecting due to temperature here, right? Next, let us see some problems here which are very important for competitive exams here, right? What is the first problem? In the circuit shown below, the current voltage relationship when D1 and D2 are identical is given by, assume germanium diodes, is given by in the figure. This is the figure which is given D1 and D2. A circuit is drawn like this. This is applied voltage V plus minus, and it's been applied. Current I is flowing like this. Current I is flowing like this, and I1 is the current. I2 is this current which is flowing towards left to right. Okay, and the similar thing here, we can able to draw here reverse saturation current. It is flowing like this, which is nothing but I01. Here also the reverse saturation current is flowing from, this is I2, but reverse saturation current is flowing from like this, so therefore it is equal to I02. So both the diodes are identical. Assume that if both the diodes are identical diodes, then what happens is, you need to remember one point here: reverse saturation currents are equal. I01 is equal to I02. That should be equal to I0. If both the diodes are identical, both the diodes will have the reverse saturation currents same. And the diodes are germanium diodes. They have been given as germanium diodes. So what is the germanium diode? Germanium diode means its eta value is equal to 1. Its eta value is equal to 1. Then what you need to find? You need to find the relation between D1 and D2, the current voltage relationship between D1 and D2. Current voltage relationship, that means current I and voltage. What is the relationship between these two, right? So from this figure you can able to see, from this figure, if you apply KCL at this point, the incoming current is equal to outgoing currents. So what is the incoming current? Incoming current is I is equal to, the outgoing currents are I1 and I2. I1 plus I2. The outgoing currents are I1 plus I2. So I is equal to I1 plus I2. Therefore I can be written as I1. What is I1 actually? It's I1 is in forward bias actually. So forward bias means I1 is called forward bias current. So what is forward bias current? According to current diode equation, we have I1 is equal to, I can write this one as I1 is equal to I01 into e power V. V means what is the potential? VD1 is a potential, because voltage across diode D1 is VD1. So therefore I can write this one as I01 into e power V, or you can write it as VD1 divided by eta VT minus 1 plus I2. But what is I2? I2 is also equal to I02, because I2 and I02 currents are I02 current is same. So therefore I can write this one as I02 from the figure. From the figure, I2 is equal to I02 from the figure. From the figure, I2 is equal to I02. So therefore again I is equal to, I can write this one as I01 into e power VD1, because it's a diode voltage, VD1, or you can write this one as a V also, no problem. No problem, we can write this one as V also, right? E power V divided by eta is 1, so it's equal to VT minus I01 plus I02. I is equal to I01 into e power V by VT minus I01 is I0 plus I0 is also I0, because both are identical, so therefore it gets cancelled. So the remaining thing is I divided by I01 is equal to e power V by VT. So V is equal to, apply natural logarithm on both sides, so therefore you get V is equal to VT ln I divided by I01. This is the voltage, the current voltage relationship when D1 and D2 are identical. So I got V is equal to VT ln I by I0. V is called the voltage, VT is called thermal equivalent voltage, I is called forward current, I01 is the reverse saturation current. So this is the equation I got. Okay. So likewise you need to do solve the competitive exam questions. Next problem is two ideal and identical junction diodes. Neta is equal to 1. Neta is equal to 1 means given is germanium diode. Given it is germanium diode, because its eta is equal to 1. Connected in series as shown below. Show that exponential e power V1 divided by KT plus exponential of minus EV2 divided by KT is equal to 2, where V1 and V2 are the voltage drops across the diodes D1 and D2. Across the diodes D1 and D2. Now let us check the same case here. There indeed it is a parallel, but here it is a series case here. Previously we have solved for parallel case, now it is for series case. Now what happens? If you solve it, what happens? For example, the diode current here this is a voltage 5 volts has been applied. So here plus V1 is the voltage. Now here this is diode D1 and the reverse saturation current of this one is like this I01, it is flowing like that, and here also I02 it is flowing like this, reverse saturation current is I02, but I02 is flowing like this, right? Now what happens? What happens here? I1 current is flowing like this. This is the current which is flowing like this, I1 current, and here the I2 current is across the diode D2, right? Next. So what happens here from this equation? What happens? This is a forward bias, so therefore I2 current is flowing like this, right? What happens? If you have this type of question, what happens? I1 is the current which is flowing from this point to this point, and I01 is in opposite direction. Okay, so here I1 can be written as I1 is incoming current and outgoing current is I01. So I1 is equal to I01 can be it can be written, and also here this is I01 and I02 both are in opposite directions. Okay, so therefore here it can be written as like this, I1 current is equal to I01 into e power V by eta Vt minus 1. This is the original expression. Now it can be written as I1 is equal to I01 into e power Vd1, because it's a diode D1, divided by eta Vt minus 1. Also it can be written as I1 is equal to I01 into e power Vd1, because it's forward bias and eta is 1, it's equal to Vt minus 1. Next, similarly right for second diode D2, I2 is equal to, it is in reverse bias, so therefore I can write this one as I2 is equal to I02 into e power, this one can be written as e power minus of Vd2, because it's a reverse bias. This diode is in reverse bias because minus sign is applied here and plus sign is applied there. So therefore it is in reverse bias. I can write this one as e power minus Vd2 divided by eta Vt minus 1. And since I2 can be written as I02 into e power minus Vd2 divided by eta is constant, I can write this one as Vt minus 1. And similarly I1 can be written as Vd1 is equal to, here it can be written as I1 is equal to I01 into e power I01 into e power Vd1 I01 into e power Vd1 divided by Vt is Kt by Q minus 1. Similarly here I2 is equal to I02 into e power minus Vd2 divided by Kt by Q minus 1. Okay, but here both are incoming currents I1 and I2, so therefore I can write this one as I1 plus I2 is equal to 0. Okay, so I1 is equal to minus I2. So I1 is I01 into e power Vd1, bring that Q that side, upper side, Vd1 into Q divided by Kt minus 1, that is equal to minus of I2 is I02 into e power minus Vd2 into Q divided by Kt minus 1. So since both are identical diodes, I told you already, both are identical diodes, reverse saturation currents are same, so therefore they get cancel. Now e power Vd1 can be written as V1, which is voltage across diode D1, V1 into Q divided by Kt minus 1 is equal to, here it is minus e power minus Vd2 can be written as V2, because voltage across diode D2 is V2, minus V2 into Q divided by Kt, minus of minus is plus 1. So therefore from this equation I have e power V1 into Q divided by Kt. Bring this equation this side and bring this minus 1 this side. What happens is plus e power minus V2 Q divided by Kt is equal to 1 plus 1, that is equal to 2. So I got an expression which is nothing but E is nothing but exponential of E or Q, both are same, into divided by Kt plus exponential of minus E V2 divided by Kt is equal to 2. So we have solved the equation, which is nothing but exponential of EV1 divided by Kt plus exponential of minus of EV2 divided by Kt is equal to 2, which is nothing but that equation, right? The next one. Assume that the current flowing through the reverse biased diode is saturated at IC0. Calculate the voltage drop across the forward biased diode. Assume Kt is equal to 26 millivolts. The same formula we need to find the voltage drop across the forward biased diode. The forward biased diode is here is V1. So we need to find voltage across V1. So if you want to find voltage across V1, the same thing we have applied there. So how to find the voltage across V1? Flowing through reverse bias diode is saturated at IC0. So IC0 means both are identical. So I0 is equal to I01 is equal to I02. So therefore both are identical. So from that below equation, you can apply here a KVL, which is minus 5. If you apply KVL for this equation, you will get minus 5 plus V1 plus V2 is equal to 0. So 5 is equal to V1 plus V2. So now you need to apply what is V1 here. If you find V1 and if you find you can able to find V2 also. If you find from this equation V1 value, you can able to find V2, right? So first find what is the V1 voltage. So already in the last already in the last class we have found what is the V1 value here, right? I0 is equal to, since we got here, since I1 is equal to the current, I1 is equal to, here the current is flowing like this I1 and the reverse saturation current is flowing like this I01, and here I02 is a reverse saturation current which is flowing like this. Okay, now I1 is equal to, I have an equation I0 into e power V by eta Vt minus 1. So from this equation, I1 is equal to, the reverse saturation current is I01 into e power V1. It's a germanium diode, already we have seen in the last class, and it is Vt. Eta is equal to 1 for germanium diode. I1 is equal to I01 into e power V1 by Vt minus 1. And similarly, what is I1? I1 is also equal to I02. We check here, both currents are flowing like this, so I1 can also be written as I02. I02 is equal to I01 into e power V1 by Vt minus 1. Both gets cancelled, so therefore I get here I1 is equal to e power V1 by Vt minus 1. 1 comes here like this, 2 is equal to e power V by Vt. So from this V is equal to Vt ln of 2. V is equal to Vt is given already, it's equal to 26 millivolts. Ln of 2 0.63, ln of 2 is 0.63, so therefore you get 0.034 volts, or that is equal to 34 millivolts. So I got here V1 as V1 is equal to 0.034 volts. Now we can able to find here the V2 voltage, since we have got 5 is equal to V1 plus V2. So therefore 5 is equal to V1 is 0.34 plus V2. So therefore V2 is equal to 5 minus 0.034. So therefore V2 is equal to, I'll get here 4.966 volts. 0.034 4.966 volts. So likewise you can able to find the potential drops across the diodes which are kept in the series. Okay, so I'll stop over here. Thank you so much for listening to the class. We'll continue next class. Thank you.